This is the Mathematics Education Podcast from mathedpodcast.com. Welcome to the Math Ed Podcast. I am your host, Sam Otten, from the University of Missouri, and with me today is Dr. Amy Ellis, who's an associate professor in the Department of Curriculum and Instruction at the University of Wisconsin at Madison. Amy, thanks so much for speaking with us.
Thanks for having me on, Sam.
We're going to be getting into Amy's recent article that was published in the Journal of Mathematical Behavior, Volume 39, and that was on quantifying exponential growth, 3 conceptual shifts in coordinating multiplicative and additive growth. But Amy, before we get to that study, I always like to put people on the map, so I wondered where you did your graduate work and what you focused on for your dissertation.
Yeah, I did my graduate studies at the Joint Doctoral Program in Math and Science Ed at San Diego State and UC San Diego. So I worked with Joanne Lobato, and the topic of my dissertation was studying how students' generalizing and justifying activities are related and mutually inform one another.
One of your past articles about teacher actions that promote generalizing is one that I've read and I've returned to, and now I'm trying to have some doctoral students read, so that's one that's really stuck with me over the years.
Oh, great. I'm glad to hear it.
So moving forward from your dissertation, you've looked at generalizing, as we mentioned, and you've also looked at relationships, linear relationships and things. This is, to me, also a fascinating area because I've worked with teachers and pre-service teachers who will look at, say, an XY table, and they'll really fixate on the X column of the table and the Y column of the table, and it seems like a pretty big shift to get them to focus across and really connect the X to the Y and how those are related. So I was wondering what it is that's motivated you to explore these coordinating growth and then particularly exponential growth.
Well, this does come out of original ideas that I worked on in my dissertation. Students do often attend to how, say, the Y column in a table is growing without coordinating that with the manner in which X is growing, unless we problematize that by actually giving students tables in which they're not well ordered, for instance. Mm-hmm. So you might have X increasing by 2, and then 3, and then 5, and then 10, and then 1, and that can kind of force that type of coordination. Mm-hmm. So basically, we were interested in conducting this study as part of a larger 5-year project. It was the first study that I did for my NSF career grant, and the broader purpose of that grant was to study how reasoning with quantities and quantitative relationships can foster more productive proving activity for students. And I had worked on those ideas a lot with linear functions with middle school students and also with quadratic function. And we were sort of interested in going in a new direction, so we thought we would explore students' understanding of exponential growth, especially since in our district students are studying that at the 8th grade level. And
then who was it that was working with you on this particular study?
So I did this work with several of my graduate students, Zekiah Osber, Tori Kulo, Kara Williams, and Joel Amadon. And Joel is actually now an assistant professor at the University of Mississippi.
Okay. Could you tell us then a little bit more about what was the data that you had to draw from and who participated in this teaching experiment that you conducted?
So let me back up a little bit and talk about the motivation for our work. Like I said, we'd done a lot of work with middle school students on linear and quadratic function and became interested in exponential function in part because there's not very much literature on that and really almost none at the middle school level. But like I said, in our district's 8th graders were studying exponential growth, and I was interested in how to better foster that kind of understanding and their ability to make deductive arguments and proofs. And the intriguing thing is that the little literature that's out there suggests that students struggle a great deal to transition from a repeated multiplication understanding of exponential growth, say 2 to the 3rd representing something like 2 times 2 times 2, to an understanding that can encompass non-natural exponents. So if you have a repeated multiplication understanding of exponential growth, then how are you going to make sense of something like 2 to the 1/2 or 2 to the 3.5? So it's hard to think of multiplying 2 by itself half a time, for instance. So the students in our district, they were working on exponential growth with classic problems like the grains of rice on a chessboard square problem, where you start with 1 grain of rice on the first square and then you double it to 2 and double it again to 4 and so on. And this quickly gets at the doubling idea, but you can see how it'd be tough to imagine non-natural exponents because that's a discrete situation.
Yeah.
Like if you think of the first square on the chessboard, that's 1 grain of rice, and then the next one is 2. But what's happening in between those states, right? When you go from 1 to 2, there's nothing to imagine. So there's no image for anything between 2 to the 0 and 2 to the 1.
Right.
So we became intrigued by this and interested in how we could help students make sense of exponential growth in a way that would actually encompass understanding those non-natural exponents. So what we did is we designed a teaching experiment and constructed a hypothetical learning trajectory, and we worked with a bunch of 8th grade students who were in regular 8th grade math class. One of the students was in algebra, but none of them had had an exponential functions unit in their classroom yet. Basically, in contrast to those typical grains of rice problems or bacteria dividing problems, we wanted to try to come up with a scenario in which students would be thinking about exponential growth with a context that was continuous rather than discrete. But that's tricky because they're middle school students, so it needs to be a simple, intuitive scenario, like preferably one that they can visualize, they can experiment with, make sense of, and mathematize. So we came up with the idea of a plant that grows exponentially. This isn't realistic. No plants grow exponentially, but we thought about it in terms of what Gravemeyer calls a realizable scenario. So it's a context that students can visualize and imagine. And we thought that trade-off was worth it because they could actually see a plant growing. We created a GeoGebra sketch with a figure of the plant that you could drag. And as you drag it to the right on the horizontal axis, you could see it smoothly growing in an exponential fashion, say by doubling in height every week. And we called the plant the Jactus instead of the cactus. That's actually a name that one of my co-authors on the paper, Joel Amadon, came up with, because the first 4 letters of Jactus correspond to several of the authors on the paper, Joel, Amy, Caro, and Tori, and us.
I think there is a lot of value in these kind of real-ish situations where it's like, yes, you can wrap your head around it, you can imagine it, it's maybe a little bit fantastical, but it can serve the mathematical purposes very well.
Yeah, I mean, one tension is whether or not the kind of non-realistic aspect would interfere with students' sense-making, and that's something we thought about a lot because everybody knows that a plant's not going to grow exponentially, but in this case, at the middle school level, that didn't really seem to interfere with their sense-making. And I contrast that to other kinds of situations that are supposedly very realistic but do interfere with kids' sense-making. For instance, there was an old problem in a Core Plus textbook that was supposed to be linear, in which students were supposed to compare the number of boogie boards sold compared to temperature on a given day. And if you actually ask students what they think about that kind of scenario, most of them realize that that's actually not going to be a linear function at all. It's probably something more like a step function. So we pay careful attention to, is the non-realistic aspect of the scenario non-realistic in a way that would sort of harm their ability to make sense of what's going on, or does it just provide something for them to explore and experiment with? And the Jactus context seemed to fit that bill.
Yeah. So you're working with these students. How many students did you have, and then how long did you actually spend with them on the teaching experiment?
So we worked with a small group of 5 8th grade students after school every day for about 3 weeks. So we met with them for approximately an hour a day. However, only 3 of the students really attended that with enough regularity to be worth analyzing. So for the paper, we restricted our analysis to those 3 students who we call Uditi, Jill, and Lauren.
Okay. I'm speaking with Amy Ellis from the University of Wisconsin about her study on quantifying exponential growth. So then, as you looked across the teaching experiment, you found 3 conceptual shifts that you lay out in the paper. So I was hoping you could just describe for us how those shifts arose from the experiment and how you kind of came to wrap your head around those shifts.
Yes, I'm excited to do that. And in order to do that, I have to talk a little bit about our thinking about exponential growth. So, can we do that first?
Sure.
Okay, so because this was a teaching experiment, one thing that we did ahead of time is we created a hypothetical learning trajectory. So, think of a basic exponential function like y equals a times b to the x. So, a would be your initial value, in this case, the plant's initial height when it starts growing, and b would be the growth factor. So, that would be something like 2 if the plant doubles in height each week. So, one thing that's special about exponential growth is that you can coordinate this multiplicative growth in y with additive growth in x. So what I mean by this is, say you think of a plant that doubles in height every week. So for an interval of 2 weeks, it will double and then double again, so it quadruples in height. And for an interval of 3 weeks, it'll double 3 times, so it will become 8 times as tall. What we were interested in is having students learn how to coordinate that additive change in weeks, comparing an interval of 3 weeks with a multiplicative change in height, so thinking about a plant that grows 8 times as tall. And one cool thing about exponential growth is that the amount of time that it takes for the plant to, say, quadruple in height, 2 weeks, is always the same, no matter how tall the plant is at any given time. So from week 2 to week 4, the plant would quadruple in height, but it would also quadruple in height from week 102 to week 104.
Mm-hmm.
As long as the interval is 2 weeks, the plants will always quadruple in height. That's one thing that we wanted the kids to understand.
Right.
And so we basically created this hypothetical learning trajectory based on reviewing literature and pilot studies, and we traced what we hypothesized would be students' transitions from a repeated multiplication understanding of exponential growth to a covariation view in which they could coordinate that multiplicative change in y with the additive change in x, and then to a correspondence view in which they could express that coordination algebraically. So they might be able to write it as y equals b to the x, y equals a times b to the x, when a is something other than 1. And ultimately, our goal was for them to understand that that quotient, that ratio of y2 to y1, is always going to be b to the power of delta x, where delta x is x2 minus x1.
Mm-hmm.
So that was our intention going in.
Okay.
So you ask, where did the conceptual shifts come from?
Yeah.
So that's the awesome thing about doing this kind of research, right? So they came from the surprises. They came from those moments when we were teaching and we thought we had a solid understanding of the students' mathematics, a good second model order for them. And then there were a couple of times where we would give a task in which I had a solid prediction that the students would solve it a certain way based on my model of their mathematics, and the students did something totally surprising. Our conceptual shifts came from those moments in the teaching experiment where the students did something that took us so completely off guard that we then had to figure out what was going on with them. One example of that is we were designing a lot of tasks to encourage students to coordinate that multiplicative growth in height with additive growth in time. And we gave them tasks in which they'd have to do this for an interval of 2 weeks or 3 weeks or 5 weeks. So, for example, say we might give the students the height of the Jactus at 2 distinct points in time. Okay, so we might give them 2 ordered pairs, say one height at 24 weeks and another height at 29 weeks. And then we just ask them, how's this plant growing? Like, is it doubling, tripling, quadrupling, something else? And the way that the students became able to solve those kinds of problems is that they would take those 2 height values, say at 29 weeks and 24 weeks, and they'd divide them. So they would divide them and get, for instance, something like 32. Mm-hmm. And so they would know that that means that the plant would grow 32 times as tall in that 5-week interval from 24 weeks to 29 weeks. So they'd say to themselves, oh, what times what times what times what times what equals 32? Or what to the 5th power equals 32? Oh, it's 2. So the plant must double every week. Mm-hmm. Okay, so at that point, one day we gave the students a table of height values, and they did something that just completely surprised us. So imagine that you just have a table of week and height values, and say the weeks are increasing by increments of 0.25. So you have 0, quarter of a week, half a week, 3/4 of a week, 1 week, and so on and so forth.
Okay.
And you have the height values at all of those times. And we gave them that table, and there was a missing height value at 0.25 weeks, or a quarter of a week. And we just wanted the students to figure out what would be the height at that time.
Mm-hmm.
They didn't have access to what the growth factor was. They didn't have access to any equation for that. They just had to figure it out from the table. So they'd had lots of problems like this, and the way that we expected them to figure that out would be something like this. Okay, the plant grows by the same ratio for any quarter week interval. So you could just take the quotient of the height values at any two other time points, like say 1 week and 1.25 weeks.
Yep.
Figure out how many times taller the plant gets.
Yep.
Say it gets roughly 1.2 times as tall. That means you can just take the plant's height at 0 and multiply it by 1.2 to get the missing value.
You would have correctly predicted my approach, because that was exactly what I was thinking.
Oh, awesome. In fact, if this wasn't a podcast, I would have asked you to do that first.
Yeah,
right?
yeah.
I would have asked you how you would
No, I actually have it on the paper here, and that was exactly what I was thinking.
That's actually really interesting, Sam, that you did it that way. That was how we predicted the students would do it, because they'd done tons of problems like that, and they'd done it that way, right?
Mm-hmm.
They totally didn't do that. Here's what they did instead. They solved it this much more cumbersome way. They wrote an equation. So the height was 1 inch at week 0, so they knew the initial height value was 1. And they wrote an equation. Height equals 1 times blank to the 0.5. Because they had the ordered pair for when the time was half a week.
All
they
right.
plugged in that ordered pair from the table at 0.5 weeks.
Mm-hmm.
Then they went through this super laborious guess and check process to figure out the growth factor in that blank, which is not easy, because the growth factor for a quarter of a week was actually 1.189 or something like that. So it was not a nice, neat, even number. So it took forever for them to do that.
Yeah.
And then once they figured out the growth factor for a week, which was 2, they could then calculate 2 to the 0.25 power to find that missing height value. So we're like, why'd they do it that way when it would be so easy to just take the ratio of 2 height values, which they've done tons of times before, right?
Yeah.
Not to mention, this way of solving it was a pain in the neck and much more time-consuming. So it was moments like that that caused us to ask a lot of questions. What was the reason? What was it about the students' thinking that would explain their surprising strategy? And in this case, for that particular example, it led us to figuring out that one of the big conceptual shifts for the students, one of the shifts we write about in the paper, is that coordinating growth in Y with growth in X for intervals that are greater than 1 is a totally different thing from coordinating growth in Y with growth in X for intervals that are less than 1. So it turns out that the interval size matters a great deal. So if you think of an expression like 2 to the third, in the Jactus context, that can mean 2 things. It can mean a static height value, so in other words, at one particular time point of 3 weeks, the height is 2 to the third, or 8 inches tall, right?
Mm-hmm.
But 2 to the third can also represent something else, which is how much taller the plant will grow, or I should say how many times taller the plant will grow in a 3-week interval. So it has 2 meanings, and the students could understand both meanings for an exponent like 3. But the amazing thing is when you switch the exponent to something like 0.25, or a value that's not a natural number, the students only had one meaning for that expression, to the 0.25. They could only think of it as a static height value, the plant's height at one point in time, 0.25 weeks. They were not able at that time to think of 2 to the 0.25 as a measure of growth, or how much taller the plant would grow in a quarter of a week.
I see. So they were, at their thinking, they had to think of it as x equals 0.25, and I've plugged in 0.25 for x in the exponent position.
Yes.
Rather than thinking of it flexibly as, this could be the multiplicative growth for any interval of time of 0.25.
Yes,
okay.
Exactly. Yeah, they could only think of it that first way, which is why they had to solve it that way. And what we began to suspect is that they didn't have images that enabled them to think about the plant growing in between the week values, because at that point, their model for exponential growth was still based on repeated multiplication, which is this inherently static image. And so what we began to realize is that in order to make that shift, students had to begin to form images for exponential growth that were not based on repeated multiplication, but instead were sort of stretching or scaling images of growth. And once they were able to think about and rely on those alternate images of growth, they were then able to begin to think about expressions like 2 to the 0.25 as representing how much the plant would grow in a time period that's less than 1 week.
Are you able to give us a little bit of a tease of some of the other conceptual shifts, and then listeners can go to the article for details on those?
So the example that I just gave was one of the later shifts, right? So that was addressing shift 3 to within units coordination. So within units coordination basically means being able to coordinate the quotient of 2 y values with corresponding intervals of time for when that time is less than 1. One thing we realized as we were analyzing what kinds of ways of thinking the students had to develop in order to make that shift is they had to go through a series of subshifts. So they had to develop that scaling image of multiplicative growth, which was one thing that I talked about. And before they did that, they also engaged in a process of reunitizing. So they were constructing new units of change in X. So they began to be able to think about things like a unit of growth for 4 weeks rather than thinking of growth repeated 4 times for that interval. So basically what we found is that the students came in to the study with an initial understanding of exponential growth that was based on repeated multiplication. And they learned how to coordinate how growth in y was occurring in ways that sort of left the x value implicit at first. And then they made the shift to explicitly attending to that coordination of growth in y with growth in x. And then they made that shift for being able to do so for lots of different corresponding intervals of time, even really big ones. And then the really challenging shift for them was being able to coordinate growth in y with growth in x for those arbitrarily small intervals, the ones that were less than 1.
So now that you've taken the time and energy to design the teaching experiment and look very closely at the students' thinking and conceptual shifts, what implications do you have to share with us, maybe for the research community, but then I'm also curious about implications for teaching?
Yeah, I think there are a couple of interesting implications for research. So one of the big implications for research, in my opinion, is simply the idea that students' thinking itself can be a source of our mathematical understanding. Like, not only of our understanding about students thinking about mathematics, but our understanding of the mathematics itself. So I strongly believe that studying student thinking can be a source of new mathematics at the K-16 level. And we found that with the work we've done with quadratic function and helping us think differently about the mathematics involved in quadratic growth. And I think that's happening for us for exponential growth too. Another research implication of our study is that it provides a model for analyzing relationships between tasks, teaching actions, and student thinking. So the 3 shifts that we reported in this paper are actually part of a larger study that presents a learning trajectory of students' understanding of exponential growth from a covariation perspective. And these days, the term learning trajectory is used to mean a lot of different things, and it's often conflated with a similar term, learning progression. And it's not actually uncommon now to see reports of learning trajectories that are based on an expert's understanding of the mathematical domain rather than on empirical findings from an analysis of student thinking.
Right.
And our work provides a model for analyzing student thinking to inform learning trajectories research that doesn't ignore the role played by tasks and teaching actions, but instead attempts to integrate those 3 in order to understand the mechanisms by which shifts in students' conceptions can come about. And another thing that we have thought about a lot in terms of implication for teaching is the value of situating students' initial thinking about functional growth in covariational systems. And we draw a lot on the work of Marilyn Carlson and also Pat Thompson in thinking about covariation and how to encourage students' covariational thinking. So encouraging the coordination of multiplicative growth in Y for corresponding additive changes in X, I do believe can help students understand exponential growth as a geometric process, and it can support flexible movement between the covariation and correspondence perspectives as students begin to write equations such as y equals b to the x or y equals a times b to the x to express those covariational relationships that they've constructed. I do think it may be more effective, especially when students are first beginning to learn about these functional ideas like exponential growth, to situate their initial exploration in continuous situations like the Jactus context, because at least it gives some sort of contextually real meaning to what's happening in between those discrete time points. Mm-hmm. And that's kind of in contrast to the more classic problems like the chessboard problem.
Yeah, and even if the students don't initially think in between, with rational number exponents and stuff, at least the context that they're working in is flexible enough to allow them to think that way. And it won't fall apart. It won't be like, oh, now that you're starting to make that conceptual shift to actually think about the continuous part of it, now we need to bring in another model to try to do that. It's like, no, you can actually still use that same model. It's robust enough to take that on.
That's right. And of course, the funny thing and the enduring challenge for us is that the big caveat that simply placing students even in these kinds of situations that we as researchers and teachers are conceiving as continuous does not in any way mean that the kids themselves are thinking about them continuously, right? In fact, in our work, they haven't been, and helping them shift from what Carlos Castillo-Garzo calls chunky thinking to smooth thinking is an incredible challenge, one that we found to be very difficult, and we're still working on ways to do that better.
Mm-hmm. Yeah, the model's not going to do it for you, but at least if the model can allow for the continuous or smooth type of thinking, that could be a benefit.
Yeah, absolutely. I think that it can afford the construction of those kinds of images in ways that other sorts of contexts or scenarios might hamper.
Yeah. I'm curious about your own next steps as you continue on this research trajectory into the future.
Yeah, we're doing a whole bunch of stuff with that. So that study was part of a larger study, and what we did is we conducted another teaching experiment the following year, sort of an iterative process. So in the first year we did this teaching experiment, we constructed a hypothetical learning trajectory before, we made an actual learning trajectory after, and then we went in with that as the hypothetical learning trajectory for the second teaching experiment. Then we did another few rounds of analysis to come up with a more finalized learning trajectory that it accounts for the students learning across both experiments. So we're in the process of publishing that now. And in general, I've become interested in learning trajectories research. And I'm interested in this line of research in part because I think there's a lot to be said for focusing our efforts on developing learning trajectories as models of students' conceptual development over time in relation to a set of tasks and particular teaching actions. We're really interested in unpacking learning trajectories as an account of change in student schemes and operations, in contrast to some of the other work that you see sometimes that are frameworks that emphasize skills and strategies. So to that end, we're currently developing a learning trajectory for quadratic functions, and I anticipate doing one for linear functions as well, and then thinking about the commonalities across all three to articulate the structure of students' emerging conceptions about function at the middle school level in general. So we're really excited about that direction. And then we also kind of simultaneously took a different direction in that we were interested in scaling up our findings to classroom settings. So after we did this series of teaching experiments for exponential functions, and we also did one for quadratic and linear, we took those findings and we did a professional development course that one of my co-authors, Tori Kulo, taught with practicing middle school teachers. And then we followed a subset of those teachers into their classrooms while they implemented some of the units that we had developed in our teaching experiment settings. And so what we're doing right now is we're currently analyzing the data from teachers' classrooms to see how well and in what ways these teaching ideas can scale up to the whole classroom setting where teachers are actually doing the teaching instead of, us as teacher researchers teaching small groups of kids.
Mm-hmm. Well, it seems like you have quite a bit going on and you have a lot of passion for these ideas. So now I'm going to ask, though, what if you weren't doing this at all? What if you were not in math education but doing something else with your life? Can you imagine something of that sort?
I can imagine it. I mean, I have to say that, I love my job so much.
Mm-hmm.
I love math ed that it's just such an incredible privilege and joy to be doing this kind of work.
Mm-hmm.
But, when I was working for tenure, I definitely had the kind of plan B options.
Mm-hmm.
Like, what happens if you don't get tenure and you have to maybe think about, rethink your life? And I think the biggest plan B, the most persistent plan B I had in mind was artisan furniture maker.
Oh.
I thought it would be great to be one of those people who makes beautiful pieces of furniture and sells them at art fairs and so forth. I'm sure that this is, a completely realistic and doable career option for me if I don't stay in math ed.
Yeah, no, that's great. Do you actually try your hand at that, or is it something like a craft that you would like to learn and try if you, had the time and energy?
Yeah, both. So I would say I'm in the
Okay.
middle. So I had a sabbatical a couple of years ago, and I started with woodworking then, and I love woodworking.
Oh,
and
wow.
I really would love to focus more on that and doing furniture making. And I just think that's a great way to sort of enable you to think artistically and work with your hands at the same time. And so it's very different from the kinds of intellectual creativity that we engage in our work, but it's still creative and it's still intellectual in just a completely different way.
Mm-hmm.
So yeah, I think that would be a lot of fun, but hopefully I'll stick with math ed for the time being too.
I've been speaking with Amy Ellis from the University of Wisconsin. Thanks so much, Amy.
Thanks very much. I enjoyed it a lot.
Thank you for listening to this episode of the Math Ed Podcast. If you'd like to support the podcast financially, please use the PayPal donation button at mathedpodcast.com.